Okay, good morning, everybody. My name is Paola Gianotti. I'm a researcher of this laboratory. And this morning, I will introduce you in a new European facility, a new lab that is on the way to be built in Germany, but it's an international facility. And since you are so young, this could be your future activity. So consider the possibility in the next year to join this enterprise. So I hope I will be good enough in attracting you toward this new activity. So where is FAIR? Sorry, this slide is very pale. Nevertheless, you can see Germany here and the other countries of Europe all around. So we are speaking about a facility that will be located in Germany. And where in Germany? Here is Frankfurt. Here is Darmstadt. And FAIR will be located here in a small town named Wixhausen. And this will be, well, over there is already a facility that is a national lab of Germany for fundamental research, mainly basic physics. This lab is undergoing a major upgrade. Here on the top of our picture is drawn the existing laboratory that is named GSI. GSI is, as I was saying, a national lab of Germany for fundamental research. In year 2003, it was decided to make a major upgrade of the existing laboratory. Germany contacted many other countries, and in 2010, they formed a convention, and the new company has been founded. It's named FAIR. FAIR stands for Facility for Antiproton and Ion Research. And you see in red what is going to be built that is actually even bigger than what is the existing. This is a scale of 100 meters. So we cannot say simply this is an upgrade of what is existing. It is really something new, not only for the size, but also because we change from a national environment to an international one. And the beam that nowadays are available in this slab are beam of any kind of ions, from protons, so Z equal to 1, to uranium, Z equal to 92. And the maximum energy available for these ions is 2 GeV per nucleon. In the future, the intensity will be from 100 to 1,000 more what is available today. And you see something peculiar here. We will have something with Z minus 1. I will explain you in a minute what I mean with this. And the energy will grow from 2 GeV per nucleon up to 35, 45 GeV per nucleons. So what is this Z minus 1? Somebody of you has some ideas of what can be a particle, an object, having Z equal minus 1? You are close to that. It's anti-proton. And since an hydrogen atom is a proton with an electron orbiting around, you were almost right. So what will be the great novelty of this facility is the possibility to have antiproton beams. And therefore, the facility will be equipped with a new LINAC. LINAC means linear accelerator. Here we will have proton produced then accelerated in this first ring, the cis-18, then injected in this big synchrotron that is actually the heart of the whole facility. Protons will be accelerated here up to 30 GeV energy. Then they will impinge here on a copper target, producing antiprotons. Antiprotons will be collected here, and when we will have enough, they will be injected in this other ring, the HESR. HESR means high energy storage ring for the experimental activity. What will be the physics program of this new big facility? This is no more a laboratory dedicated to one topic, but it will be a laboratory with a very broad range of topics to be studied. This is why, as I told you, I'm pretty sure that some of you could find here some interesting aspect to study. So, first of all, as I was saying, there will be ion beams, but also beams of radioactive ions. So, beams that are very unstable and that can decay immediately or soon via nuclear reaction. And this can be used to study the structure and the dynamics of nuclei. We know quite a lot about nuclei, but not everything. And by producing nuclei in exotic states or in unstable states, we can learn something more about their nature. We will have, as I was saying, this new beam of antiprotons that probably when the facility will be in operation will be the only antiproton beams available all over the world. And the purpose of this beam will be to study hadron structure and the dynamics of quark and gluons. I will explain you later because I will mainly focus on this pillar of the scientific program of FAIR. Then there will be a program for studying relativistic ion collisions. So ions will be produced and accelerated at high energy and then smashed one against the other. Actually, probably you already know and you heard yesterday a colleague of mine was speaking about the ALICE experiment. ALICE is studying ion collisions. In the LHC, lead ions are accelerated at very high energy and then smash one against the other. Here, there will be a similar kind of research, but with a different technique, because there will be just one beam accelerated and then smashed on a fixed target. So the research field is similar, so the study of this plasma of quarks and gluons, but using a different technique and having a different phase space of this new status of matter. Then there will be also activity in the field of atomic physics. And the idea is to check the so-called plasma physics. So to produce plasma of ions with high density and in extreme conditions and making interaction between plasma and laser light. And this is something that has many practical applications, for instance, for studies of confinement that are extremely important on the way to produce a fusion reactor. And then there will be also study of electrodynamics and, how to say, laser of extremely high power will be produced and studied there. So this is the, let's say, shopping list of the facility, all aspects that will be studied there. Now let me open a parenthesis, because as you have seen, I was starting speaking about GeV per nucleons, but I don't know if you are familiar with these units and this concept. So I would like to be a bit didactical now and give you some basic information of things that are not strictly related to my presentation, but will help you in understanding all the talks of this Masterclass event. So, first of all, let me introduce you with Mr. Electron Volt. The electron volt is nothing else a unit of measurement. And what we measure with electron volts? We measure energy. So, I hope you know that the energy normally is measured in joule, or joule if you prefer, in French. And 1 electron volt corresponds to a tiny value in joule. It's just 1.6 10 to the minus 19. So 1 electron volt seems to be something very, very, very small. And this is the energy, the amount of energy that an electron gained when it moves across a difference of potential of 1 volt. So if we have here an electron emitted by the surface of a capacitor with a difference of potential of 1 volt, when this electron arrives on the other plate, it will have an increase of kinetic energy that is exactly 1 electron volt. Oh, and we can have multiple or sub-multiple of this quantity. Normally we have, since this, as I told you, is a very small quantity, we speak about multiples of this quantity. For instance, what I will call MEV is 1 million of electron volts. MEV means millions of electron volts. We can have also GeV, giga electron volt, that means billions of electron volts, or of even TeV, tera electron volts, that means 10 to the 12 electron volts. So let me remind you also some basic concept of relativity, because I was mentioning at the beginning that we accelerate in fair these particles at very high energy. It means that for these systems we cannot apply the classical mechanics, but to describe their motion, the dynamics of the interaction, we have to use the relativity and the corresponding formulas. And the basic formula of relativity is this one, related for a particle, his mass, with its velocity or momentum, and the energy. And we know, this is a famous formula that was written for the first time by Albert Einstein. This formula said that the energy, the total energy of a relativistic system, a particle or something else, is the sum of the momentum squared plus the mass squared. So if we measure the energy in electron volts, as I was saying in the previous slides, then it turns out that the momentum will be measured in electron volt over c. And so for velocity, we speak about electron volt over c. And for energy, it turns out that energy are measured in electron volts over c squared. Here I have also reported some formula that you will see in my or other talks, in which you have, for instance, the definition of the quantity beta. Beta is the velocity of our particle, our system, divided by c, that is the velocity of light. So is the fraction, how close is the velocity of a particle to the speed of light? Because if the velocity is close to c, this number will be close to 1. So a particle with a beta 0.9 means it's a particle that is running very fast. It's running close to the speed of light. Gamma, okay, don't want to enter too much into details, but it is another parameters that is a combination with a beta squared. The energy is here. Once you replace this gamma in this formula, you can write the energy in this way as the mass times gamma times c squared. And again, the momentum can be written as the mass times gamma times beta times c. And beta can be also, you can play yourself with some algebra. You will see that you can derive beta as P times C divided by the total energy. Okay. So I already told you that 1 electron volt is the energy gained by a charge, a unitary charge, traversing a difference of potential of 1 volt. Okay. This corresponds to 10 to the minus 19 joule. Okay. But how much energy is this? I mean, I would like to give you the feeling of what it is. So in kilogram, if we consider, for instance, a B, we can weight a B, the mass will be around 1 gram. So a B of 1 gram have an energy that is very huge. It's almost 10 to the 32 electron volts. So it's really a big amount of energy. And this is for a bee at rest, lying on a flower. If the bee is flying, let's say with a speed of 1 meter per second, then, sorry, here I forgot to translate, ape in Italian means bee. The energy, the total energy of the bee, if we use this formula, is this one, 1 millijoule, something like this. So 6, 10 to the 15 electron volts. That if we compare that with the energy of a proton inside the LAC is this big accelerator that is nowadays running at CERN in Geneva, you see that the energy we have for a proton in the LAC is not even the energy of a bee flying at speed of 1 meter per second. So you may guess, so you are not so good enough. You are producing something that finally is not so much energy. Nevertheless, if you consider that inside the LAC, we have 10 to the 14 protons. This is a very big number. And you multiply this for the energy of each of them, you arrive to a total energy that is 10 to the 8 joule. So remember, 1 electron volt is something very small, 10 to the minus 19 joule. In the LAC, we have a total energy that is, 20 millions of joule. It's like a big truck, of a mass of 100 tons traveling at a speed of 120 kilometers per hour. You can make the exercise and calculate the energy. You will arrive to this amount of total energy. So this is to say that finally, within the LAC, is like smashing 2 trucks one against the other and studying what's happening. Okay, now that you know everything about MEV and the units we use to measure mass, momenta, and energy, let me give you another basic idea that is the mass scale. So on this axis, I've identified where is lying 1 MeV, where 1 GeV, where 1 TeV. And you see that the mass of, well, let me say something before, that physicists are very lazy. So normally, in the formula I was showing you here, we make a very, a simplification. And we place C equal to 1. In this way, the formula became very simple. And we have the same unit for energy, for mass, and for speed, for velocity. So by using this convention, we have that the mass of an electron, you know the electron is the basic unit for charge, it's 0.1 mega electron volts. The mass of the muon, that is a companion of the electron, but heavier and more unstable. While the electron is stable, the muon, after a while, decay, transform in an electron, has a mass that is 2,000 bigger. Then we have, for instance, the mass for the proton and the neutrons that are the basic constituent of nuclei. That is more or less 1 GeV. This is an approximation. If you look in textbooks, is 0.98, and there is also a tiny difference between the mass of the neutron and the mass of the proton. But it's just to give you an order of the scales. We have other particles like the Z. This is the mediator, the boson mediating the weak interaction that has a mass of 100 GeV, and the energy we have nowadays in the LHC is 14 TeV. Let me also give you an hint of typical length scale. Yesterday, my friend Hannes Mescal was explaining you how particle detectors works, which kind of detector we used. And normally, the spatial resolution, so the precision we can get in measuring the position of a particle in one of our detectors is at the level of microns, so 10 to the minus 6 meters. Compare this with the wavelength of light. Visible light has wavelengths that is going from 300 up to 700 nanometer. A nanometer is 10 to the minus 9 meter. The dimension of an atom is an order of magnitude smaller, is 1 Armstrong, 10 to the minus 10. And you see that since the dimension of an atom is an order of magnitude less than the wavelengths of visible light, we cannot study atoms, we cannot see atoms with visible light. In order to see atoms, we have to use something that has a resolution power, so the capability to enhance smaller details. So, for instance, electronic microscope or particle accelerators. And to see protons, you see the dimension of a protons is more or less 1 Fermi, that is 10 to the minus 15. This is why to study protons, to study particles inside the protons, so the basic constituent of matter, we cannot use the light because we don't see nothing. We have to use something else with a capability to resolve smaller details. Let me also give you some basic scales for times. 1 millisecond. Sorry, here is an error, is 1 microsecond. This should be the Greek symbol mu, sorry. 1 microsecond, so 10 to the minus 6 second, is the time that an electron takes to travel in 5 centimeters of air. Again, Hannes yesterday was describing tracking detectors. The typical time we have to measure for a drift, the traveling of an electron in argon is at the level of microsecond. While an electron that is relativistic, so that is traveling with a beta close to 1, it travels at the speed, it takes 1 nanosecond, so 10 to the minus 9 second, to travel over a path of 30 centimeters. But we can have even smaller times. For instance, a B meson, don't care what it is, a B meson, but it's a very unstable particle that immediately decay, transform in something else. And this crazy particle has a lifetime that is at the level of picoseconds, so 10 to the minus 12 seconds. So all of this is to say that in fundamental research, in particle physics research, we have to deal with things that are really, really small and tiny. And this is a sort of, from my point of view, contradiction with the dimension of the object we are using for studying this tiny object. Because I don't know if you have been already in Daphne and you have seen already our accelerator and our detectors. The size there is something big. The scale is 10 meters or so. And if you will visit CERN, you will see something even bigger. So the overall tunnel of the LHC is something around 30 kilometers. So, and the detector, the Atlas detector, is a sort of building of 10 stairs. So in order to study things that are invisible to the normal light, we have to build objects that are very, very huge and complex. And why we build these crazy objects so big and so complicated? Because the ultimate goal is to study what matter is made of. This is something that is not studying only today. There were people already in the past trying to understand the nature of matter. The ancient Greeks, the philosophers of ancient Greek, they believed that nature was made with 4 elements that were fire, air, water, and earth. Then along the century, for instance, in the 19th century, science evolved and we knew that there were more elements. Here is not visible, but this you can find it on the Wikipedia, is the first attempt made by Dalton to classify the elements known in nature. And if you will look to this table, you will see that there are basic elements like, for instance, gold and silver and copper, but there are also elements that are not fundamental, like, for instance, water. But this was a great attempt to classify the elements and started something that then was concluded, let's say, in its full glory by this physicist, Mendeleev, at the end of the 19th century. And you see, he was compiling this table, the table that nowadays is known as the periodic table of elements. And you see, here the Greeks believed nature was made with 4 elements. Here the number is more than 100. So it was clear already at that moment that nature, these elements were not the fundamental constituent of nature. There was something below that, combining together, were producing the different elements. Nowadays, we know which are these basic constituents of matter. We know that there are, I was already mentioning electrons and his friend, his big brother, the muon. There is also a bigger one that is named lepton tau, and each of them has a corresponding neutrino. Matter is made by quarks, and there are, as for the leptons, 3 families of quarks with funny name up and down, charm and strange, top and bottom. And then there are forces, and forces are mediated by particles. We call them bosons. This gamma is the mediator of the electromagnetic interaction. Z and W are the mediator of the weak interaction. And G is the gluon, the mediator of the strong force. Oh, what particle physics then is doing? We are trying to find out the basic constituent of matter. And try to understand how they bind together, which is the force and which are the rules of this force binding the basic constituent together. So we study the interaction, and we mainly observe scattering, as I was saying, in the LHC. We smash protons or lead ions, or here in our accelerator we smash an electrons with his antiparticle, the positrons. And by means of this interaction, we produce new particles, and we study them. And we study them using those kind of detectors that Hannes was describing. So we have to build detectors, we have to build accelerator. We can have primary beams and secondary beams also obtained not only from accelerator. For instance, a beam of neutrons or neutrinos can be get from nuclear reactors or natural sources like, for instance, cosmic rays. And as I was saying, the physical process, the interaction of these particles between each other and the ordinary matter is made with ad hoc detector. And the information we get are collected and studied by means of sophisticated analysis. Yesterday, Pasquale was showing you the huge computers, for instance, that are used to analyze the data in the LHC. But even here in Frascati, we have our own computing center that is meant to do this kind of activity. Okay, this was a sort of introduction. Now I would like to move to one of the pillars of the FAIR, the facility for antiproton and ion research that is on the way to be built in Germany. I will speak about antiprotons because it's my field of research. I'm working there, so it's where I'm really found out. So I would like to tell you why we are using antiprotons that are particles that in nature are not existing. We have to produce them, spending energy, and we have to confine them in a place where there is no matter, because you know that when an antiparticle meets ordinary matter, a particle, it's annihilate. It means that we have a sort of explosion, they transform their mass in energy, and then this mass is again converted in other particles. Oh, the antiprotons, as I was saying, is the antiparticle of the proton. The protons, to our knowledge, is a stable particle. Therefore, even the antiproton should be stable, apart from the fact that when it find matter annihilate. And therefore, we use this capability, and this is, sorry, there is an error in the sign, sorry. This should be negative, and this should be positive. So this is a proton, and proton has a positive charge, not negative, sorry. I will correct in the slides I will give you. The antiproton has exactly the same mass, but negative charge. And normally the antiparticle of a particle, for convention, is indicated with a bar on top of that. So when you see the symbol P with an horizontal bar on top, this means antiproton. If you want to indicate, for instance, an anti-neutron, you will write N with a bar on top. As I was saying, by smashing protons and antiprotons, you get a burst of energy that then convert in other particles. The existence of the antiprotons was postulated by Paul Dirac in 1933 during his Nobel lecture. Paul Dirac got the Nobel Prize because he was predicting the existence of antimatter, and in specific the anti-electron, the positrons. But he was elaborating more this concept, and when he presented his Nobel lecture, he was proposing and suggesting the existence of the antiproton that finally was discovered in 1955 in the US by a group of physicists that then got the Nobel Prize in 1959. From the discovery on, antiprotons have been used a lot to do fundamental research, and there were antiprotons collider at CERN, and also in the US at the Fermilab laboratory. And by studying proton-antiproton interaction, we were able to find out, you remember, those bosons mediating the weak interaction, and also to discover recently the top quark. This was when the collision took place at a very, very high energy. But there were other machines using antiprotons at a lower energy, and LBL, BNL, CERN, Fermilab. And the most famous was this antiproton storage ring that was in operation at CERN from 1986 up to, if I'm not mistaken, 1996 or so. And by using this very clean beam of antiprotons, because I was working there at that time, we were performing spectroscopy of many particles. Nowadays, there are also beams of very, very low energy. Probably you heard, because there was recently a new paper published on the Nature journal about anti-hydrogen. So colleagues at CERN are trying to create not only anti-particle, but really antimatter, as your colleagues were mentioning before. So means an antiproton around which there is an anti-electron, a positron orbiting. This has been produced. Many anti-hydrogen atoms were formed. So, and they are nowadays studying the characteristics of this antimatter in order to understand if there are differences between matter and antimatter. This is for the past. What about the future? The future of anti-proton physics probably, well, the P-bar-P collider that was available at Fermilab has been stopped last year, so let's say that it is not clear if there will be a future for antiproton physics in the US and even at CERN. So the only real and future of antiproton physics is in this medium energy range. That is exactly the FAIR facility that I will describe you in a minute. And for FAIR, there is also a program similar to that ongoing at CERN to study antimatter, anti-hydrogen. So you remember I was showing you the whole layout of the FAIR facility, but where the antiprotons will be used is this ring here, this accelerator that is named high energy storage ring. The antiprotons will come here from this side, and then will circulate within this ring. This ring have two straight sections, and in one of the two straight sections we will have a target, and surrounded by a complex system of detectors I will show you in a minute. This machine will have a very high, let's say, performance. The production rate, so we will have around 210 to the 7 interaction of antiproton per second. the momentum, so the speed of these antiprotons could be varied within 1 GeV over C up to 15. The number of antiprotons stored here is 10 to the 10. You remember I was telling you that for protons at CERN we have 10 to the 14, that is even bigger. But consider that producing antiprotons, protons are available in nature. Antiproton we have to produce, we have to store, collect, cool, and so on and so forth. So 5 10 to the 10s will be really a world record. We never get such a number of antiprotons all together. As I was mentioning, there will be this internal target. This tube is, let's say, the antiproton beam, and these dots falling down is a sort of spray of hydrogen droplets that are sprayed inside the beam direction, and in order to have interaction, and all around we will have detectors. We will have a very high definition of the velocity and then of the energy of antiprotons. So the uncertainty on the energy will be at the level of 10 to the minus 5. That is really something never achieved. Oh, let me now again jump and making you something more didactical. Our goal in this kind of experiment is to study strong interaction. You probably have already seen that there are many forces in nature. We have gravitation that I think you are more familiar with, and gravitation is something that is related to mass. Every particle having a mass is subject to gravitation. And if we say that gravitation interaction has a strength of 1, you see how the others interaction are strong, let's say, with respect to this. Weak interaction that is responsible for radioactive processes and, for instance, the process of fusion within the sun has a strength that is 10 to the 25 with respect to gravitation. The electromagnetic interaction is even stronger, but the strongest is this that we call actually the strong interaction that is responsible for binding protons and neutrons within nuclei. Without this force, protons will repel each other because they all have the same charge. So from the point of view of the electromagnetic interaction, they cannot stay together. So there should be something else, that is the strong force, that is, how to say, winning against this electromagnetic repulsion and making them stay all together. Another thing I would like to point out is the range, how far the force can be felt. Consider that gravitation has a range that is infinite. The weak interaction has a range that is very small. It's 10 to the minus 18 meters. The electromagnetic interaction, again, has the gravitational interaction, and they also behave in the same way. R means the distance from the source of the force. The strong interaction is so strong, but has a range that is very short, is 10 to the minus 15, that, if you remember, was what I indicated as the dimension of a proton. So outside the protons, we don't feel any or only remaining of the strong interaction. So this is why we have to go really to distances so short if we want to study the strong interaction. So the strong interaction is responsible to bind, as I was saying, protons and neutrons in a nucleon, and at smaller scale is the force carried by this boson we call gluon that holds the quark together to form protons and neutrons and other similar particles that we call altogether hadrons. Okay, the strong force has high strength, and therefore the objects that are bound by this strong force, and we call them hadrons, are the force is high enough to produce new massive particles. I mean, if we succeed in breaking one proton, breaking one hadrons, we will produce new particles. And this is a typical characteristics of the strong force. There are also other property of strong force. One, the more important from my point of view, is color confinement. So I was mentioning for the electromagnetic interaction that is something related to the charge. So a particle having an electric charge can feel the electromagnetic force. There is something similar in the strong interaction, what we call the color charge. Every quark can have, and this color can have different values. But finally, the object, like the protons and the neutrons, are not colored. So the color is something that is hidden, let's say, within the hadrons, but does not appear outside. And the theory that is trying to illustrate and describe the strong interaction is the so-called quantum chromodynamics. This chromo means that there is this color charge that is what is feeling really the force. This is a blackboard that Frank Wilczek wrote during his Nobel lecture. He got the Nobel Prize for Physics in 2004. Okay, you see, I don't want to enter into the details, but in principle, this formula is very simple if you know the mathematics behind, but I don't care. And that's it, he was saying. Nevertheless, the point is that this equation, this formula, leads to an equation that cannot be solved exactly. And then it's not exactly that's it, because we then have to figure out how to describe the system's experiences strong interaction. Therefore, there are other approaches, different models that are less rigorous than the QCD, that try to describe the systems, the particles. Well, the title is completely wrong, sorry. What I would like to tell you here is only that this theory, the quantum chromodynamics, not only predict the ordinary particle, let's say, states of a quark and an anti-quark, or three-quark states. Because what we see nowadays in nature are mainly two kinds of particles. We name them mesons, if they can be considered a pair of a quark and an anti-quark bind together, or baryons, if they are a three-quark states. But nothing prevents to have something more exotic, like a system where there is also a gluon participating, or a sort of molecule made by two CC bar states, or even a glue ball, a blob made, a particle made only by gluons. And what we are trying to do in our experiments is to confirm this theoretical picture and to demonstrate that those exotic states are existing. And there are already candidates. This is the list of non-ordinary particles that we have below 2 GeV in mass. Nevertheless, since it's very hard to study this particle, not all of us are convinced that we have observed this exotic. And look to this picture. In red, and so the lines are the theoretical prediction made using different approach, QCD or other models. And the blue points are, or these with errors bars, these are the experimental measurement. So you see there are many lines that have never been observed. So no experiment was measuring a state here or there. And there are states, for instance, this, that have not been predicted by the theory. So the message I would like to give you is that strong interaction is still not well understood. So this is why we are studying and continuing doing our research in many labs all over the world. There is also this problem, I was mentioning the color confinement. So that means that none of the particle we observe as color, the color is confined within the hadrons. There is also another aspect that is we have this quark that have a fraction of the electric charge, while all the particles we see in our world, they have a unitary charge. So, and these gluons, these massless particles that is mediating the strong interaction, we have never observed. So, if QCD is the way to describe a strong interaction, we have to have a deeper understanding, clarify those aspects that are not so clear at the moment. Another point I would like to mention is what is related to the Higgs boson. You have certainly heard that CERN has announced the discovery of the Higgs boson. I don't want to enter into the details. Maybe Gino, that will speak afterwards, we will say you something more. But the only message I would like to give you is that even if we nowadays know that the Higgs boson exists and this theoretical description on how particles get mass has been almost confirmed, the Higgs mechanism is giving to the particle only a fraction of their mass. If we simply sum the mass of the quarks, we will never arrive to the value of the proton mass, because there is a lot of dynamics within the protons. I mean, the quarks are not staying in the proton without doing nothing, let's say, but they are interacting, and this interaction is affecting the mass of the particle. Therefore, we have to study the strong interaction in order to understand how the dynamics affect the mass. And then there is, okay, this I will skip because we are a bit late in time. So let's try to summarize. I know I have gave to you a lot of concepts, so let's try to summarize. Nowadays, the prediction that the quantum chromodynamics gives in describing the fundamental particles are not so bad. We have something around precision, an agreement between experiment and theory at the level of 10%, let's say, at least at the scale, at the energy of the proton mass. Can we be satisfied of this agreement? 10% is not so bad. Nevertheless, as a caveat, I would like to remind you that a theoretical framework that was called the Ptolemaic system, that was predicting the position of the planets and of the satellites in our solar system, was giving predictions that were accurate, more or less at the same level, 10%. Nevertheless, this was wrong. And only keeping studying, we understood that the Earth was not the center of the solar system, but the sun was the center of the solar system. So my message is we cannot be satisfied saying, okay, we almost understand the general behavior of the theory, we have to keep studying in order really to check if what we know up to now is correct or not. And in order to do these studies, there are many techniques you can use. I was already mentioning CERN is studying proton-proton interaction or ion-ions interactions. Here in Frascati, we are using electrons and anti-electrons. At FAIR, we will use antiprotons because we believe that antiprotons are extremely powerful. A proton is a state of 3 quarks, and antiprotons has the corresponding antiquarks. So with this picture, I mean that when you have a proton and an antiproton coming close each other, this quark annihilate, and they produce other particles. So you transform completely your mass into energy, and you can access other systems. And here I'm showing you the 2 mechanisms we use to produce a certain state. We want to study, for instance, this particle G. We have the interaction proton and antiprotons, and this particle can be produced with another one that is compensating for and balancing the energy and the momentum, or we can form this directly and with other, and by, how to say, studying one or the other kind of reaction, we can understanding something on the property of the particle. Okay, this I will skip because it's too technical, it's for physicists. Another thing I would like to stress is that if you remember, when I was describing the accelerator, the HESR, where we will do our activity, I said I was stressing that we will have a very high precision in knowing the energy, the velocity of the particle. And this could be achieved with what we call the cooling of the beam. We will cool the beam. When in 1983, Carlo Rubbia was awarded of the Nobel Prize, there was another guy sharing the Nobel Prize with him, that was Van der Meer. And this guy was mainly a physicist of accelerator. You will heard a lot about accelerators. Massimo today we will describe you how accelerator works. And this guy was, together with his colleagues, inventing a cooling system, a system to give the particle in the accelerator all the same energy. This picture is showing you the spread of velocity of an antiproton beam before the cooling in red and after the cooling in blue. So you see that finally you have a beam where all the particle has exactly the same energy. That is crucial when you would like to make precision measurement. Okay, this too technical. Okay, what we would like to do then in FAIR, but also in other experiments all over the world, is to study the structure of the hadrons and how they interact inside the particle. You can use different kind of technique, I've already said. And in this slide, you see what we call the phase space of our experiment. This is the range of mass we can explore. These 2 dotted lines are the boundaries, the limits within which we will move. And in this energy region, the zoo of particles we will be able to study is quite large. So the experiment on the HESR will be really an experiment with a wide range of activity. Here I'm reporting from different kind of reaction, for producing different kind of reaction, which are the rate we are expecting. And the idea, as I was mentioning, you see here, for instance, we have a good agreement between prediction of the theory and measurement, but above this value of mass, you see there are few states known, there are a lot of prediction, but we need data in order to fill up the gap. And the experiment that will do this kind of research is named PANDA. PANDA stands for antiproton, you see P with bar, so antiproton annihilation at Darmstadt, because as you remember, this facility FAIR is on the way to be built in Darmstadt, this small town close to Frankfurt. We will build a detector that is a sort of paradigm of a particle detector. So here we will have the antiproton beam entering. In this point, we have this spray of particles of hydrogen atoms, and therefore we will have the interaction with the antiprotons. This will produce a wide number of secondary particles that then will be detected with this set of detectors. We have a first one with a magnet producing a field. This is a cylinder, and we have a constant field within this cylinder. The strength of the field is 2 Tesla, and this magnet is superconducting in order to consume less power. And inside there are different kinds of detectors. Here we have a second magnet. This is a dipole. A dipole is like a simple, has only 2 poles. So a particle traversing a dipole, if it is charged, it is deflected left or right. It depends on the sign. And even there we have other detectors to measure. We have tracking detectors. This means detectors for measuring particles with charge. We have different kinds. We have what we call a vertex detector around the interaction point, and we use silicon detectors for this kind of measurement, because these are the more precise that can give you this resolution of micron I was mentioning before. Then we have tracking detectors that are gaseous detector. Then we have a detector that identify the species of particle, protons, electrons, or muons, so on and so forth. And you can see how many we have. We have, finally, detector for neutral particles that are the so-called calorimeter. This is a picture of the collaboration. Can you find me there? I will help you. I'm staying there. So you see, we are quite some people, 500 almost, coming from 18 countries all over the world, because you have seen the detector we would like to build is quite huge. So we need a lot of people building all the components. This is why, and we need people preparing the software, the programs to analyze the data we will produce and to make simulations. We have also a lot of good technicians helping us. And so to summarize, we have a new project, an international facility on the way to be built in Germany. The physics program of this facility is quite wide. It spans from atomic physics, nuclear physics, and then particle physics. The aims, finally, is to study the strong interaction. The strong interaction, we know a lot about it, but not all. Therefore, this is why fundamental research all over the world is still keeping on studying. The heart of this facility is an accelerator with a circumference that is 1 kilometer. If you compare to the LHC, is not so big. But what is peculiar is the variety of beams we will have. We will have ions beams, we will have these antiprotons. And if you want to have more information, this is the website you can visit. Thank you for your attention.